Hello, welcome to this second video where I'm using Trinket and using Python and the turtle module to create particles just for a laugh. So welcome back if you've seen the first video and you want to see what's going on next. Okay, so or welcome if you just want to watch some Python. Right, my trinkets. So that brings me back to my home folder on Trinket here. And trinket particles tutorial. Right, so I'm just opening up the code from the last video, and what I've got to make sure I do is not overwrite this code. Right, so there are our particles. This is Bert, by the way. Hello, Bert. He's that little turtle there. And these are particles on the Bert's array. Just a coincidence that I called it that. So no relation to Bert. These Berts are these particles. Right, so let's first copy this code. So I've just asked Trinket to copy it, and now I'm going to call this video 2, and then just change the name from copy of and save that. Okay, so now I can change all of this code, and the code from the first video will be intact, and people can go and find that from the first video in the description. Okay, so I'm just going to make the font a bit larger so you can see. So we've got these 3 particles, and what we want to do in this video is maybe get collisions working with each other, but also maybe with the sides. We can bounce off the sides, or maybe, as I suggested in the last video, if we go off the side, the particle appears over here like Pac-Man. It kind of like wraps around. Right, first thing, I want to make the background a different color. So to do that, like we created this turtle object here, Bert equals turtle dot turtle, which just uses the turtle module to instantiate or create a turtle object and then store that object in Bert. And once you've got it stored in a variable, we can then change its shape and its color and make it go to different places on the canvas. We're going to say screen, what should we call our screen? Adrian. Don't know why that name came to my head. Adrian equals turtle dot, not turtle, but screen, capital S, brackets, and now we can ask Adrian to be a different color. If you're a logical person, and you probably are, you'd write color just like we did for Bert to change him to green, but that won't work. You have to, when you're dealing with a screen object, you have to use BG color for background color. So then we can make this a lovely shade of gray. If I make all the red-green values the same, we should have a nice, it's very classy gray. I don't like the outlines of the particles. They should be white now. So let's go to this for loop. So this loop goes around 3 times, and each time it creates a temporary turtle, changes its shape to a circle, its color, things like that, gives it a velocity, gives it an acceleration, and then this is a very important line, it then adds that, or appends or pushes that turtle, that temporary turtle, to the Bert's array. So what we do here will be true for all of the particles we make. So let's make their pen color, which if you just assign it a pen color after you change the color of your turtle, it will give it an outline, that color. So this should make them stand out a bit more. That's much better. You notice how they judder? Let's turn off or comment out the pen up. So now, when we play, they should leave. I don't have to save it to play, it's just a habit. There we go. Oh, that's really cool. So it leaves like a record of where they've gone. The first thing actually that happens is the particles are made there, then they go to a random place, and then we give them a random amount of acceleration. So what might be nicer is actually is to not do that. So I've just commented out a random position. So at the start, they all start in the home position right at the bottom. Now, notice this going on. The juddery effect seems to be because when we move them, we're moving them on the X and then the Y and then the X and then the Y. What we really want to do is do it together And if you notice the lines, when we had the goto working, actually, put that back on, we had the random positions assigned at the start, those lines are completely straight. So I think the goto function works using like vectors, which is what we want to work with. It should have much smoother movement. So let's go into our Euler physics system. Here it is. And these two lines, 40 and 41, this is where we're setting the x and the y position. So let's comment those out and just use one goto call. So get hold of our turtle, goto, and we can just reuse this code, this bit here, because this is the new x position. And I'll just paste the same thing and just change the x's to y's, and that's the new y position. Done. Was it that simple? Right, so what we're looking for now is when we run it, you should have nice smooth lines. That's much better. Our particles are looking a lot better now. That's really nice. Okay, save that. Right, so let's get them bouncing off the walls. I'm in the Euler physics system function. Let's just label what this is. This is the friction. So if I turn that off by commenting it out, whoops, just press Command Save to save it. Press play. Now they should just travel forever, according to Isaac Newton's ideas. There we go. Right. So let's turn off the lines so that we can turn them back on later on to make it look really nice. Treat ourselves later on. So what we want to do is get it, should we get it them wrapping around like Pac-Man? Okay, so let's write this function over here. Let's just, zombie out the random positions at the beginning. Before our particle system, we'll have a function. So this is the Pac-Man wrap around. So define new function. We'll call it packwrap. And what is it going to do? I think we're going to call it on the main function like we call the physics function, and then we could pass in a turtle, and then we could just check where that turtle is. Has it gone over the window boundary? If it has x and y, then reposition it. Easy peasy. So we'll call that turt, and we'll say if turt, now we need its x position. Let's start with the x position. So that was x core, I believe. So that function just returns the x coordinate of our turtle. So if its x coordinate is less than minus 200 seem to be the edge. So let's just give ourselves a value, edge, and we'll say 150, so we can still see our turtles kind of disappear and things for testing. So if it's less than minus edge, then we want to set its, or go to, that's what we want to say. So turt go to edge, so that's the other edge, so that'll be plus 150, so it'll be over here, and its y position wants to be the same. So should we store that at the beginning, or just say here turt? No, what, we'll store it at the beginning. We'll say my y equals turt dot y core, y coordinate. And while we're doing that, we'll do the x coordinate as well. So my x equals turt dot x core there. So now we can say if my x is less than minus edge. Okay, that's nice. And then nice and tidily, we can say, just go to your y. Don't worry about the y position. We're just changing the x position. Right. We kind of want an else, don't we? So elif, else if, my x is greater than the edge, then turt go to minus edge my y. So if your x position is greater than the edge over here, so greater than 150, go to minus 150 and keep the y the same. Lovely. Right. Can we continue this? So let's just comment this. So check x bound, and this will be check y bound. And we just need to change the x's to y's and y's to x's. Done. Done? Is that really done? Actually, I think I can anticipate. I'm kind of modeling in my head. I can see some problems. So let's just see what happens. So this is our main gain loop. Or simulation loop. Just call it loop. Main loop. So this goes around and it calls the physics on each turtle, and then we want to do packwrap. Is that what I called it? And then pass in each turtle. Right, save that. And then, stretch the back and press play. So something's happening. They're kind of hitting the boundary and then getting whisked all over the place. And we've definitely lost one particle. That's amazing. Right, so let's just check our code first of all. If my x is less than minus edge, go to the edge, my y. Oh, I can see one thing that's wrong. Go to, this should be my x, and that should be edge. This should be minus edge, and this should be my x. So my little bit of changing the x's to y's was wrong. I didn't think it through. Yeah, we want to, when we're checking the y boundary, we want to keep the x's the same. Because when we're checking the x boundary, we want to keep the y's the same. So we're just dealing with x's. Right, so let's just look at that. If my y is less than minus edge, go to edge. Yep, that kind of checks. It checks out. Okay, so stop that and then play it again. Still going to be a bug. Okay. Something a bit more like we're expecting is happening now. But what's also happening is that the way Turtle works is that when you call goto, when you call this function, it moves that particle visibly across the screen so you can see it. And we are moving at speed 100, I think. So I set, when I create all the turtles, the particles, yeah, I set the speed to 100. Let's just set it to 0, just to see what happens. So it's actually much better because that's weird. It looks like sometimes that they kind of bounce off. Weird. Anyway, we'll keep that to 100. But what we want to do before moving them, so in our packwrap, what we want to do is make our particles invisible. We want to say turt hide turtle. Then do all the moving. After we finish with the moving, turt dot show turtle. And that's working, but it's now making them kind of like flash, because it's hiding it, showing it every single frame, which seems to really slow down. our application. So unfortunately we're going to have to call that every time, or type that in, paste that in every time we call the goto, but now only when we call the goto. And so before we call the goto, we hide it. And what we could kind of also do is make speed 0, so that they instantaneously move. Oh, have we already done that? No, I changed it back to 100. So let's do that as well. Turt speed 0. And then we need to change this back to 100. But I think I can just... Oh, maybe I should have just called that the speed once at the start. Anyway, let's write now turt.speed 100. That's not great, because what if I change that number over here and then I forget about it here? So I should do something better than that. I should say speed or rig speed. So when we go into packwrap, what we want to do is say a rig speed equals the turtle's current speed, which I think if we just write speed without any arguments, it just returns the current speed, I think. You know what we could do? Let's just write here to console, print Bert speed. Does that work? Have we got Bert? Let's ask Bert. Oh yeah, actually it'd be interesting to see what is Bert's default speed, because we don't change good old Bert's speed. None. Okay. Let's try that again. Bert speed 100. None. So that function does not return the speed. Anyway, right. Let's just write global rig speed, and we've got a rig speed there, and then we can create an original speed for our Berts up here. So original speed for our Berts, our particles. Should not call them Berts, particles, because they're on the Berts array. So damn it, where's a rig speed? A rig speed equals 100. So I can set that here, and then I don't need to set Bert speed anymore. But when I'm setting the particle speed, I want to pass in this variable, so that if I want to change their speed, I just change it once up here, and then it changes automatically there, it changes automatically here. That's good programming practice, else I'd have to remember to keep track of all that, on top of all the other changes that I make. So speed is reset there. This is working really nicely now. I can kind of see the logic of it. Oh, I just wanted to explain this global business. Because I've made this variable orig speed outside of this function, I've made it here, so part of like the original level of our program. When we go into a function, orig speed would be just local to that function. So you use the global keyword in Python to say, oh, you don't use a temporary variable called orig speed, you use the global variable, i.e. this one that's globally made at the level of the program. Okay, so a bit of a scope there about where variables can be used. Right, so I've done a little bit of programming there. We need to save and just see if those few changes actually work. That looks a lot better. We're still getting good performance, and our particles are zipping all over the place. Okay, right. So let's write another function to get them bouncing off the sides. So we'll call this bounce. So we want to pass in a turtle again, And then we want to say if, you know what, let's just grab the coordinate stuff and the edge stuff from the previous one, previous function, sorry, and then we can say in a very similar way, if my x is less than the edge, sorry, the minus edge, minus 150, then we want to change that particle's velocity. So if it's hitting the left like this one, we want its y to continue going down, so we don't want to change the y velocity, we just want to reverse the x direction. So if it's, yeah, minus to a plus. So the turt's, what did I call it? Vel x? Let's go and have a look. Yep, vel x. Times by minus 1. So if it's a minus number, it will now be a positive number. Maybe that's a nice way of doing it. Right. Else if, or elif, my x is greater than the edge, then, wait a minute, we just want to do exactly the same thing. It's going to be plus 1, it's going to be a plus number if it hits this side, so again we just want to times it by minus 1 and it will reverse it. So actually we can just say if it's less than minus edge, or my x is greater than the edge. Oh, that's nice and efficient and beautiful. Right. Let's press. Oh, I was going to test that out. Let's test that out. So instead of calling packwrap, we want to call, what do we call it? Bounce on our turts. Save that and run. That was brilliant. We got one hitting the side. Are you going to hit the side? I don't think we've got any friction anymore, have we? Yes! And it hits the side and continues. But now we haven't got the packwrap off. They just continue. Right, so let's go back up to bounce. And we just want to copy this code. So this is bounce off x edges. And we want to bounce off the y edges. This time I want to be careful. Last time with the wraparound I went wrong with my x and y. So if my y is less than minus, oh that's down here, less than minus edge, or my y is greater than the edge, then the y direction just wants to be flipped. So times equals minus 1. So if it's a minus number, it'll become positive, and if it's a positive number, it'll become minus. I love that idea. The symmetry in the maths there, that's really nice. Right, let's obviously add 4 more particles and save it and run. So we've got many more particles. Off they go. And they're all bouncing off the sides. That's really nice. Yeah. Right, could we do something like, let's make a few less. Let's go back to 4 because it's already hitting the performance. What if we change the original speed to 4? What does that look like? A little bit juddery. What about 0? I think that's a bit smoother actually. So we'll keep it to 0. Now, if we hit the side, could we change its color? So bounce. So if it hits the X, we could say turt dot color, make it go blue, 0 red, 0 green, 200 blue. And if it hits the top, we could make him go some kind of yellow, 200, 200 on the red and the green. Save that, stop there and play. Yeah, that's really cool. That's really nice. Okay. Actually, I want them to go green again when they hit the top. I guess what you could do is just swap its colors out or something like that. Oh, we need to make the is the pen color white to begin with? Right, then you need to set the pen color again afterwards. Okay, so we'll do that. Pen, oh, turt, pen color 255. I wonder if this hits performance because I'll do it every update. Yeah, that seems to really hurt performance. So we only want to do that after we've bounced it. That's much better for performance. Right. Collisions between particles. Do we save for the next video? Maybe we do. Was there anything else I want? Oh yes, let's just turn on the trails. That'll be fun. So I'm going to turn off pen up when we first make the turtles. It'll be interesting to see where they go. Because now it's kind of like drawing an interesting pattern, which I guess you could analyze, or you could fiddle around with the colors and the attributes, the accelerations and things, and get some interesting patterns going on, especially if you're not affecting friction. Let's just turn on the friction again, which was in our physics system. Will they hit any of the sides? That's the thing, no. So let's turn it right down to 98. So it's going to be like they're sliding around on ice, I guess, but there is a little bit of friction. And they've hit the blue side, lovely. So there we go, that's nice. So what I'm really tempted to do, will this work quickly? I think I only need 4 or 5 lines of code. If I press the screen or tap the screen, if you're on touch screen, it'd be nice to add give all of the particles some random force. Let's do that. Now, then you can kind of play around with it. Right, so let's go down to the main loop. So what we want to say is Adrian.listen. Yes, Adrian was our screen object. So to start listening to events like clicks or mouse presses or key presses, things like that, so they're events, things that the user does to interact, we need an event listener, which we've now got. It's as easy as writing whatever your screen is called, dot listen, and then what we need is a callback function. So we want to say if there's a click, so on click, go and run a function called, I don't know, let's call it explode, because I imagine the particle should explode outwards. So that's going yellow because we haven't defined that yet. Notice when you use a callback function, you don't put in the brackets there, you just write the name of the function, which is weird and I hate doing it, but that's what we have to do, guys. That's what we have to do. So define explode, and then we want to get all of our birds. So for we'll call it a turtle in our birds array, iterate over all of those, and we want to say the turtle's acceleration on the x equals, and then we can ask for a random int, and we can go between minus, let's go 50 and 50. And then we want to do, can I do that in Python? Can I kind of use white space? And then I want to do the same for its acceleration on the y-axis. What was I just thinking? have I named the acceleration correctly? Yes, acc x, acc y. Let's just remind myself what I'm doing for later. Remind my future self what this means. So add random force to all particles on the Bert's array, or list, because we're in Python. Right. Right. Save that. Will that actually work? I don't know. Let's run it and find out. We'll run it without the pen. So that's where we make turtles, because I want to treat myself if it actually works. Right. Bad input on line 109. So let's go to 109. Is this our callback? 109. Oh. Turt.acx equals. Oh, right. So I can't do that. I have to put it all on one line. I'm sure I could break it up another way, but I'm not familiar enough with Python yet. Okay, by the way, you might be thinking, if you didn't see the first video, if it's a long time since you saw it, r.randint, you might think, what on earth is that? Well, at the start, I've imported the random module, which gives me the randint function. Try and find an example of it. Yep, randint function. And this will return a number between whatever you put in as arguments. So it'll give me a random integer whole number between -10 and 10. And we just have to put r, or the name of the module here. But I've put as r, so I don't have to write random dot, I can just write r dot. Okay, right, so let's save it and run it. And there should still be a bug when I click the screen. Notice I have to hit it twice. You need to hit it once to get focus on the screen, and then again to actually click. Right, explode takes exactly 0 arguments, 2 given. So let's go to my explode function. There it is. So it's got 0 arguments, but the on-click event takes 2, or passes to, or returns to values, and they are the X and the Y position of the mouse, which is quite handy, because you could use that to maybe grab hold of a particle. Right, so I just need to put in an X and a Y, or MX, MY, that'll do, to remind me that it's the mouse position, X and Y, or the finger position if you're tapping on a touchscreen. Right, save, run that again, and I can't foresee any bugs this time. So, we've got friction working, we've got collisions working. If I tap the screen, yes! Our particles get a lot of acceleration. And it looks like you can kind of trap them in the margins if you add too much acceleration. So let's take that down by a factor of 10 and see if we get some more appropriate acceleration. Yeah, that's much nicer. It's like you're kind of like shaking them when I'm tapping. Lovely, right, let's leave it there. I have no idea how long this video has been going now. Something like half an hour or 40 minutes, something like that. Again, leave any comments if you've got any suggestions for this project, or any questions or requests or anything, and I'll try and answer as soon as I can. Next video, collisions between the particles. Yeah, and then something else. Okay, thank you very much. Thank you very much for watching. See you again.